Okay, guys. Having looked at the Haber process and the contact process, I thought that it would be good to do past exam questions, PPQs, on the Haber process and the contact process. So, what I've done is that I have looked for a paper, a past exam paper. This is the summer paper. Let me just so it is summer, May, June 2016, strand 41. So this is the paper that we are looking for. We are going to deal with. So the question, this is a question on the contact process. So we are looking at the contact process. This is a question on the contact process. So it's good to look at the contact process as it is. So it says sulfuric acid is produced by the contact process. The steps of the contact process are shown. So we have got these steps, right? And obviously the starting materials should be obviously your raw materials. So this is your raw materials. Okay. So we have got step number 1, step number 2, step number 3, step number 4. So sulfur is a common starting material for the contact process. Name a source of sulfur. So the source of sulfur should be in, let me use blue pen. I can get it to work. So the source of material could be fossil fuels. Fossil fuels, right? With other books will talk about sulfur beds, or they'll talk of other things, but a good source of sulfur can be actually fossil fuels. So, right. So obviously, your raw material in this case will be obviously sulfur. Your starting point will be sulfur and oxygen. Okay. So oxygen is obviously your oxygen is obviously from the air. All right, so I think I've talked about more than I should talk about that. Then this is step number 1. So we go to step number 2. Describe step number 2, giving reaction conditions and the chemicals equation reference to this. Oh, okay. Reaction. So here you got sulfur dioxide. Obviously, when these two react, you get sulfur dioxide. We already know that this reaction should be a reaction between, and you are forming sulfur trioxide. So it's a sulfur dioxide plus oxygen, and you get sulfur trioxide. Right, and always remember to balance this equation. I do forget to do that sometimes, and all of them are gases. Right, so all of them are gases, and balance the equation. And the other thing that you have to show is that it is a reversible reaction. So it is a reversible reaction. So you've got to show that it is a reversible reaction. So you need to put the, this arrow or this symbol for reversible reaction. Right. And also that remember that this is the reason why this is called the contact process. It is the reason why it is called the contact process, because the reaction must happen in contact with a catalyst, and the catalyst is vanadium 5 oxide. So remember that that's the catalyst that is actually that is used, right? And the question says describe by giving the reaction conditions. So this is one of the conditions, and you are supposed to give so what does that state do? Remember that it is a catalyst. So what does it do? Increases rate of reaction of of reaction. So that is the function of this catalyst. So it increases the rate of reaction. So already we have done one thing that we've done in the chemical equation. So we have got, I think we have done that, and we have done at least one condition that we need a catalyst. And the other one is that we need a pressure of around what? 2 atmospheres, right? It is a low pressure. We don't need a high pressure. Remember that because we don't need a high pressure, because at this low pressure, the yield of this is actually high. Remember that we said that the yield is anyway 99%. So it is quite a high yield. And remember, because pressure costs money, we don't need to have a high um, pressure. So it is just a pressure of 2 atmospheres. And the other thing is that we need a temperature of 450 degrees Celsius. And this temperature, remember that it is a compromise. It is a compromise. Right. Why is it a compromise? Because remember that if you make the temperature too high, the reaction is going to be fast. But but then what is going to happen? Because this reaction is actually, maybe I should use a different pen. This reaction is actually endothermic, right? And because it is endothermic, what happens is that the yield is going to decrease at a high temperature. And at a low temperature, what happens is that the rate is going to be too slow, right? Although you're going to have a high yield. So we are actually caught between a rock and a hard place. So we need to make sure that the temperature is actually a temperature that that we can be able to use, which can give us a high yield and a sort of a high yield and a sort of a high rate of reaction. But remember that this temperature of 450 is actually a compromise, right? And let's see if we have covered everything. Where do we get the marks, right? The marks will be, obviously we should be able to get a mark for showing this reaction. Okay, let me just get the red pen, right? So we get a mark for showing that it is a reaction, and also a mark for showing that it is a reversible reaction. That is 2 marks already, and a mark for each of these. So we have got already 1, 2, 3, 4, 5 marks. So and remember that you should always write down the units. And a lot of students do forget to write down the units, degrees Celsius here. So write the units. And if you do not put down the units, you might not be able to get the marks. So yes, so this is a 5-mark question, and that's what you get. So step number 3 involves adding sulfur trioxide to concentrated sulfuric acid. So remember that this sulfuric acid is actually concentrated, very important, right? It is concentrated to form oleum. And if you're going to form the oleum will be, this is an easy the formula for oleum is actually easy to remember. One thing that you need to remember is that you've got 2 hydrogens here, so you just put 2 hydrogens, and you have 2 sulfurs, right? So this sulfur, and you have got 4 plus 3 oxygens, so it is 7. So this is obviously the formula for oleum, and you get your 1 mark there, right? Your other mark. So let's go to the other question. Dilute sulfuric acid is a typical acid. So obviously you should know that it is an acid, so it behaves as an acid. Okay, so a student adds excess dilute sulfuric acid to a sample of copper 2 carbon give 3 observations that are going to be made. So now we've got your sulfuric acid. So remember that it is dilute plus copper sulfate, right? Is it copper carbonate? Sorry, copper carbonate. Copper carbonate, right? And you are going to get right. So remember that if this is a reaction between an acid and a carbonate, a metal carbonate, and you already know that you should get a salt. So we are going to get a salt, which is copper sulfate, right? And you are supposed to get carbon dioxide, so plus carbon dioxide plus water, right, plus H2O. Right, so this is the reaction, guys. So what are we going to observe, right? You can already see that there is a gas that is going to be formed, so that one of the observation should be what? Should be one of the observation should be bubbles. So you're obviously going to see bubbles. Okay, bubbles. I don't know what I'm writing there. Right, you're supposed to see bubbles or fizzing, if you like, because a gas is being produced. And the other thing that you're going to observe is that the solution, the thing is going to form a substance that is blue. This is a blue solution. So a blue solution is going to be formed. Solution is going to be formed. Blue solution appears. Right. Why does it appear? It appears because this is actually copper sulfate is actually blue. Aqueous copper sulfate is blue. That's very important to remember. And the other thing that you're going to observe, remember this is solid and you have added an excess of this. It means that all of this is going to be used up. So what happens is that the solid, oh dear, don't know what's happening here. Oh, now I've made it too big. The solid is used up, or it dissolves. The solid dissolves. So the solid copper carbonate is going to just give the names of the products. We've already done that. I don't know what I've done here. All right. The products that you are going to form are the products that you will form. We've already mentioned these products are the salt will be your copper sulfate, and your carbon dioxide, and your water. Those are the products that you are going to form. Let me wrap this. Okay, so remember that there are 3 products, so you've got to make sure for you to be able to get the 3 marks, you're supposed to right, the products. So it says products here. So you've got to put all the three products. If you put only two products or one product, you're not going to get the marks. So concentrated sulfuric acid has different properties to sulfuric acid. When concentrated sulfuric acid is added to glucose, which is this one, steam is given off and the black solid is formed, named the black solid. Now, what you need to know is that concentrated sulfuric acid is actually a dehydrating agent. It is a dehydrating agent, and because it is a dehydrating agent, what it does, it removes the water from this. And when water is removed, which is the H and the O, remember water is H2O, right? So it means that you have removed the hydrogen and the oxygen, so what is left is actually the carbon. So here the black substance is going to be the carbon, right? What reaction type or what type of reaction has occurred? You can call it dehydration. Oh dear. You can call it become too big. This thing is a little bit. It's not cooperating with me. You can call it. Come on. This thing has disappeared for some reason, or it is frozen. Okay. Yeah. So, okay. You can call it. Let me go there. Right. Let's go back. So you call it dehydration. That's the name of the reaction. Let's go to the next question. I didn't want to make this video to be too long, but let's see if we are going to finish in the next 5 or so minutes. Right. We are not going to do this question now because that's not what we are looking for. So this question is not what we are looking for. We are looking for ammonia. The Haber process, no, ammonia is made by reacting. And this question, before I go on, it is actually from 2016, October, November, strand 41. So ammonia is made by reacting nitrogen with hydrogen to form. So these two are your raw materials. They are your raw materials. I don't know what's happening with my computer today. These are your raw materials. So yeah, okay. So I need to change the thickness of my pen. These are your raw materials. So what again you need to remember is that you write a chemical equation for this reaction. Already you know that you've started with hydrogen and nitrogen, so you've got your nitrogen plus hydrogen, right, is going to give you nitric acid. Hydrogen. I have no idea what's happening. You're going to get keeps doing that. You're going to get ammonia, right? And also remember that it is a reversible reaction, and you need to balance this, and you are going to have 3 hydrogens and 2 of this, and always put this, show that it is what reversible, put that sign. Okay, right? So that you get your 2 marks. Name the raw materials materials from which nitrogen and hydrogen are obtained, right? We already know that these are obtained. Nitrogen is obtained from the air. Oh dear, from the uh, this you get it from the air, right? And this right, you get it from the air. Remember that we talked about liquefaction of air. After air has been liquefied, what is going to happen is that you're going to separate the nitrogen and we are going to separate the nitrogen from the liquefied air by fractional distillation. And we say this is obtained by cracking of crude oil, of crude, uh, cracking of crude oil. Right. Okay. State the temperature. Uh, state the temperature. State the temperature of. All right. State the temperature of pressure and pressure used in this. Right. Remember that the temperature should be 450 degrees Celsius. Right. And the pressure. We said that again, this temperature is not too high, not too low, right? It is actually a compromise, right? It is a compromise. If we make this temperature too high, maybe let me push it up there. If we make the temperature too high, we might have a problem, right? I don't know what's happening now. I'm failing to control this. It's just doing whatever it wants. Let me just back up here and do right, and then increase the size. Okay, now it's not increasing the size. Okay, let me go up. All right, so it is a compromise now. And then the last thing that we need to know is the pressure. The pressure is going to be quite high. It is 200 atmospheres, right? And we can get away with this pressure, which is quite high, because our yield is quite low in there. Remember that. And also, if we increase the pressure, remember that we have got only four rather moles in the reactants and 2 in the products. So it means that a higher pressure will favor the forward reaction, thereby increasing our yield. So yeah, right? So those are the 2 things. So the last thing that we want to talk about, the other question, is that um, we want to talk about, we want to look at this question. Ammonia is a reaction also made when ammonia carbonate decomposes, when this decomposes. And notice something, it is a reversible reaction. And if you're going to notice, we have got a solid here, and we have got what? Gases that you are going to form. So the reversible reaction is this reaction is reversible and can reach a position of equilibrium. The graph shows how the yield of ammonium at equilibrium changes when temperature and pressure are uh, uh, with temperature and pressure, with an increase of temperature. What is meant by the term equilibrium for a reversible reaction? So equilibria is, I've started doing that again. Equilibria is one when you have in an equilibrium reaction, we have got the rate. We have 2 marks. So the rate of the forward reaction and the backward reaction. Backward reactions are equal. So we have got to talk of the rate, always in the question, the rate of the forward reaction and the forward and backward. I've left out something there, which is what? Reaction are equal. So, but the concentrations of the reagents, which is the reactants, remains constant. So what is not constant? What is the rate is going to be the rate of the backward reaction and the forward reaction are going to be the same, and also, but then the reactants when the product's concentration remain unchanged or remain constant. Using the information from it from the graph, explain whether the reaction is endothermic or exothermic. Well, let's look at the graph. Right. What is happening if you increase pressure? Right. If you increase pressure, what happens when pressure is increasing at 100 degrees Celsius? Right. The yield is the yield of ammonia is going to decrease, so it's lower. But at low pressure, the yield is high, and this is understandable, right? The yield is high. So what happens? Yield, we can actually say that. Explain what using information from the graph. Explain whether the reaction is endothermic or exothermic. Okay, right. So let's look at the temperature. Right. If you look at the temperature, you are going to notice that from at low temperature, your yield is low. And at high temperature, your yield is high. So you've got more of this. So you've got more of this at low temperature. So if we take, let's say, this point, right? At 100 degrees Celsius, the yield is lower than at 300 degrees Celsius. So temperature actually, rather, yield increases with temperature. Yield increases with an increase of temperature. Right, that is sorted out. Let's look at the last bit. State and explain the effect of increasing the pressure on the yield of ammonia in this reaction. Now, we have already noticed something, right? That whenever you increase, let me just wrap this. Whenever you increase the temperature, so we've got 2 points, this point and that point. So you can see that in both cases, and if we go up there, right, in both cases, at low pressure, yield is going to be high, right, for both cases, whether the temperature is 100 or whether the temperature is 300. Or here, at high pressure, the yield is low. And we can see the reason why. It is very clear that here, right, the thing is that the reactants are solid and these are gas. So the only thing that can be compressed is the um, products. And because you can compress the products, right, what is going to happen is that because you can compress the product, what is going to happen is that equilibrium is going to shift towards the reactants because you are causing this to collide more. They become too close together and the collisions are going to increase, and therefore the backward reaction is going to be favored. Therefore the yield is going to decrease. So let's write that yield decreases with an increase of temperature, or with an increase of pressure, right? And why, right? There are more moles in the products. The products and the reactants. Right, and the last bit is that position of equilibria will favor the side with fewer moles. Right. So that will be your answer. So you get, remember that it is 3 marks. So you get a mark for saying that, and another mark for saying that yield is going to decrease. You get a mark for saying that more moles in the products than the reactants. You're going to get a mark, and you're going to get another mark for saying that the the equilibrium is going to favor the side with the fewer moles, which is, I'd left something there, which is the backward reaction, So yes, guys, this is it. This is the video. I've made it too long. It's like 33 minutes. I should have done it in 2 videos. But yes, because I needed to explain a lot of things. If you've got any questions, right, remember to comment below. Okay, thank you. Bye.